Okay, good morning. We'll create another video now. This is Chapter 7, Section 2. And in this, we're going to be discussing confidence intervals. So, CIs for the mean, for the population mean, when the population standard deviation is unknown. So, CIs for mu when sigma is unknown. All right, so here, the important formula that we're going to be using, well, let's see, oops, just to cross out everything there. What we're going to be using here, well, is a new distribution. It is, I'm going to draw it basically just like the Z distribution, and this one is going to be the T distribution. And this one is similar to the standard normal distribution, or the Z distribution, the Z curve. It is a bell-shaped curve. It is symmetric about the mean. That means the mean is right here in the middle, and the right and the left half are identical mirror images of one another. The mean, the median, and the mode are all equal to 0, and are all at the center of the distribution. And then finally, even though it looks a little bit bad right here, it's supposed to be like this. The curve never touches the x-axis. So all of those 4 points are what it has in common with the Z distribution. The T distribution is slightly different from the Z distribution in the following ways. The variance is greater than 1, right? So how that affects our particular, for our particular value, what that means to us basically is that the values are going to be slightly different. Okay, and then what else? The T distribution is actually a family of curves based on the concept of degrees of freedom, which is related to the sample size. Okay, so that means that depending on the size of your sample, you actually are using a different one of these curves in the distribution. So for larger and larger sample sizes, the curve kind of becomes a little bit more spiked at the center, and is more close in terms of its structure, its curvature to the standard normal curve. Okay, so basically here it looks like I'm drawing a couple of different curves, and I am. I'm drawing various different degrees of freedom for these curves. All right. Oh, and like it says here, yeah, the third feature is it's not exactly the same as the Z distribution. It's based off of the sample size, but as we let that sample size, as we let n approach toward infinity, that Z curve, or sorry, the T distribution looks more and more and more like the Z distribution. So let's just go into a simple example of how we use the T distribution table. Okay, so I have here a handy pull-out copy of Table F. This is located at the back of the book, and there are numerous locations online where you can bring up a copy of the T distribution. So we're going to look at example, whatchamacallit, 7-5. We're looking here on page 384. And in this one it says to find the T subscript alpha over 2 value for a 95% confidence interval when the sample size is 22. Okay, so the thing I guess that we didn't mention yet is the degrees of freedom that's based on the sample size, but we didn't say how it was based off of the sample size. Here is the relation right here. The degrees of freedom is the sample size minus 1. So that is kind of something that we see that's similar. That is the denominator. That's what we divide by in the traditional computation for sample variance and sample standard deviation. But anywho, let's see, we're going to find t subscript alpha over 2. So we're still using this alpha over 2 notation. Okay, and we want a 95% confidence interval. So make a note of that. And then here we have n is equal to 22. All right, so let's go over to our table and we'll reconvene there. Okay, so here is a copy of Table F in our textbook. It's Table F. It's the t distribution. Along the side here we have df, right? So that's our column for degrees of freedom. And then across these columns at the top here, there's these various different sub-designations. So for the moment, we're going to ignore this business about one tail and two tails. Okay, so you'll notice that the one tail and two tails, there is a relation between them. But for the moment, we're going to just disregard those. We're talking about confidence intervals. So we're going to be looking at confidence intervals. And the way this works is really simple. What did it tell us? I think it said 95% confidence interval. Remember, that's a kind of our default value. That's our go-to value anyway. So here we are. We're just going to slide over to the 95% confidence interval column right there. And then what was the second thing? The sample size was 22, but make sure we don't go all the way to 22. We're going to go to 21 for the degrees of freedom. So n minus 1 here is the degrees of freedom. It's 21. So notice here is our value. Am I pointing at the correct one? It is this one. No, wait, sorry. 21 degrees of freedom is 21. Confidence level is 95%. And so the value that I'm seeing here is 2.080. Okay. Okay, so where we came down was t subscript alpha over 2 was 2.080 for 95% confidence interval for a sample size of 22. So meaning we had our degrees of freedom was equal to 21, right? So one thing that I wanted to just kind of show you, if my doc cam will cooperate with me, is here looking at one of these columns, notice that the values are decreasing. So here, focusing in on the 95% column, notice that the values are all decreasing as we go down further and further. Let's see, all the way down to the, hard to see here, all the way very down to the very bottom here. They're lower and lower and lower values. And then notice at the very bottom, we see that familiar value again, 1.960. And notice here, that's the z distribution using infinite number of degrees of freedom. All of those are our familiar z values. So that's kind of a nice handy place that we can access those critical z values as well. All right, let's move on to the important formulas for Chapter 7, Section 2. The margin of error here is very similar to the margin of error for the confidence interval for mu when we know sigma. Here we don't know sigma, so we don't get to use the z distribution. We don't have critical z subscript alpha over 2's. We have critical t subscript alpha over 2's. And then the second thing is we don't know sigma, right? So we can't multiply by sigma. So instead we have s. But we still do take into account the size of the sample, so we will still be dividing by the square root of n. So notice here, if we just swap out t with z, and instead of s, if we put in sigma, that's the exact same margin of error for the confidence interval for mu, except if we know sigma. Okay. And then the second thing is, I'll just say it the same exact way that I said it in the last section. I knew there was a reason I wanted to do it this way. It's that mu is equal to chi bar plus or minus e. All right, well, what do I really mean by that? I mean, on the one hand, e is bigger than chi bar minus e, and on the other hand, mu is less than chi bar plus e. So just to reiterate, mu is bigger than chi bar minus e, and mu is less than chi bar plus e. So this is the left-hand endpoint, and this is the right-hand endpoint of our 95% confidence interval. We'll go to an example in the next video. So let's stop there.